All right, welcome. Today, we are going to break down one of math's most powerful shortcuts, exponents. If you've ever seen those little numbers just kind of floating next to the big ones and wondered what's going on, stick around. We're about to make them make perfect sense. So, what exactly are exponents? You might also hear them called indices. Well, really, they're just an awesome way to simplify math. Seriously, think of them as a cheat sheet for doing the same multiplication over and over again.
At the end of the day, they just save us from writing out these long, tedious problems. Instead of writing 2 times 2 times 2 like 7 times, you can just write 2 to the power of 7. It's so much cleaner, way more efficient, and honestly, it's the foundation for everything we're about to get into.
So here's our game plan. We're going to start with the main idea. Then we'll build our basic toolkit with 3 essential laws. After that, we'll dive into some of the weird cases that can trip you up. Then we'll put it all together to simplify some expressions, and for the grand finale, solve a few puzzles. Sound good? Let's do it.
Okay, first things first. Let's load up our mental toolkit with 3 fundamental laws. If you can get these down, you're honestly halfway there. They're the key to everything else. So law number 1 is the product law, and it's super straightforward. When you're multiplying 2 terms that have the same base, that's the big number, the a, all you do is add the exponents together. So if you had a to the 7th power times a to the 4th power, you just add 7 and 4. You get a to the 11th. That's it. Simple.
Next up, the quotient law, which is, it's pretty much the exact opposite. When you're dividing terms with the same base, you just subtract the exponents. So a to the 7th divided by a cubed becomes a to the power of 7 minus 3, which leaves us with a to the 4th. Makes sense, right?
And our final core tool is the power law. So what happens when you have a power that's being raised to another power, usually with parentheses like this? You just multiply the exponents. So if you've got a cubed, and that whole thing is raised to the power of 4, you just do 3 times 4 to get a to the power of 12. And there you have it. That's our basic toolkit.
All right, now for the stuff that can really trip people up. We're talking about the weird exponents, the ones that don't seem super intuitive at first glance. But don't worry. Trust me, they follow a really clear logic once you see how it all fits together.
Let's kick things off with the zero exponent. This is a simple rule, but it is so important. Any number, as long as it's not 0, raised to the power of 0 is 1. That's it. Unity is just a fancy word for 1, so whether you have 5 to the power of 0 or 1,000,000 to the power of 0, the answer is always 1. It's a great little rule to have in your back pocket. Okay, next up, negative exponents. This is a big one. It is so tempting to think this means you're going to get a negative number, but nope, that's not what's happening at all. A negative exponent is basically an instruction. It's telling you to flip the base to the other side of the fraction line, and then the exponent becomes positive. So just like you see here, a negative 3 flips to become 1 over a cubed.
And that brings us to fractional exponents. Now these can look really intimidating, but they're actually just a really clever way of writing roots. The number on the bottom of the fraction, the denominator, that tells you which root to take. So if it's a 2, it's a square root. If it's a 3, a cube root, and so on. The number on top is just a normal power, just like we've already seen.
Okay, so we've collected all our tools, we've got the basic laws, we've stared down the so-called weird cases. Now what? Well, now we put it all into practice. Let's take a kind of tricky-looking expression and see how we can use our new rules to tame it.
All right, take a look at this. Yeah, I know, at first glance this thing looks like a bit of a monster, right? You've got powers raised to other powers, you've got a 0 exponent in there, and even a fractional one for good measure. But with the rules we just learned, this isn't a monster, it's just a puzzle.
But here's the thing. You just have to break it down, step by step. So first, that 3 squared cube, that's our power law. 2 times 3 is 6, so we get 3 to the 6th, which is 729. Okay, next piece. That 5 to the 0, that's our 0 rule. Anything to the power of 0 is just 1. Easy. And finally, 81 to the power of a half, that's a fractional exponent, which just means the square root of 81, which is 9. Now, you just do the basic math, and that whole scary expression just boils down to 717. See? Not so bad.
All right, time for the final boss. Well, not really, but we're definitely leveling up here. We've seen how to simplify expressions. Now we're going to use our laws to do something you see all the time in algebra, finding a missing variable. We are going to solve for x.
So here's our puzzle. We've got this equation, and we need to find the value of x. But look where it is. It's stuck way up there in the exponent. How are you supposed to solve for something that's literally floating up in the air like that? It seems impossible, but there's a really elegant trick to it.
Here's the secret. The trick, the absolute key to unlocking this whole thing, is to get the bases on both sides of the equation to be the same. Just look at the numbers we've got, 9, 3, and 27. What do they all have in common? They're all powers of 3. We can rewrite 9 as 3 squared and 27 as 3 cubed. This one move is what cracks the whole puzzle wide open.
So here's how it plays out. First, we rewrite everything using that common base of 3. Then, we just use our exponent laws to simplify each side. We get 3 to the power of 2 plus x on the left and 3 to the power of 6x minus 15 on the right. And now for the magic moment. Since the bases are the same, they're both 3, the exponents have to be equal too. It's the only way it works. So we can just pull the exponents down and solve them like a normal simple equation.
And just like that, after a little bit of standard algebra, boom, we have our answer. We used our exponent laws to take this really complicated-looking equation and figure out the missing piece. The value of x is 17 over 5. So what's the big takeaway from all this? It's that exponents aren't just some random list of rules you have to memorize. They're a really consistent, logical system. And once you have this toolkit, you can simplify expressions and solve equations that probably seemed impossible before. So I'll leave you with a little something to chew on. If you know what a negative exponent does, and you know what a fractional exponent does, what do you think happens when you combine them? What kind of instruction is a negative fractional exponent telling you to do?